So good morning. The aim of these 3 lectures will be to try to show you how one can apply all these ideas on active system to cellular problems. I will try to give 1 lecture today on the mechanics of cells, and then tomorrow and Wednesday I will talk about mechanics of tissues. So today I start with the mechanics of I will try to alternate between the board and the slides because I'm unable to draw anything. So today is the mechanics of cells. Now this is kind of the sketch of a cell. If you look at it, it's full of compartments here. These compartments are called organelles. And what I will focus on is not these organelles. The most famous one is the nucleus, which is here. I will focus on the space between the organelles, which is called the cytoplasm. And inside these cytoplasms, you have filaments, and these are these filaments that control the mechanical properties of the cells. This system of filaments is called the cytoskeleton. And it's made of 3 types of filaments. 2 of them Joanny talked about. One of them is actin. One of them is microtubule. And the third one is called intermediate filaments. Now, if you discuss mechanical properties of cells, almost everybody agrees that the only type of filament that counts is actin. If you put cells under very strong deformation, the elasticity might be controlled by intermediate filament, especially if you look at neural cells, for instance. So during this lecture, I will only talk about actin. Actin interacts, as Joanny said, with many, many proteins. There are 3 types of protein that I want to discuss. Proteins that control the polymerization of actin. So these are actin polymerization promoters. Molecular motors. And the one that interact with actin are called myosins. And the last type of protein that I want to talk about is cross-linking proteins, proteins that take these filaments and cross-link them into a gel. So this is the 3rd type of protein that I will care about. So what I want to do is show you briefly how you can describe actin, how molecular motors can interact with actin. I'll talk a little bit about what we call active gel theory. And in the end, what I want to discuss is what's called cytokinesis, which is the last stage of cell division when the mother cell divides into 2 cells. So that's what I want to discuss today and to discuss within the framework of this active matter theory. So let me start by the actin cytoskeleton. And by actin filaments. So I have the slide. So the actin protein is this protein, which is sketched here. It's what I will call the monomer. It has a size which is 5 nanometers. There are two properties that I want to insist on. The first one is that it's not symmetric. It's polar in this direction. There is a pocket here. And in this pocket, you have an ATP molecule. These monomers assemble. They form a filament which is here. This filament is made of two linear actin filaments that wind into a helix like this. The assembly is polar, which means that all the monomers assemble in the same direction, and in the end you have a polar filament. So that's the first property that I want to keep, that actin is a polar filament. It's chiral also, because I have these two protofilaments that turn around one another. It seems that most of the properties of cells don't care so much about the chirality. So in all of the following, I will ignore the chirality of actin. The second thing is that these filaments are not permanent. They polymerize on one end, and they depolymerize on the other end. So I told you that actin was polar. There is a plus end, which is sketched here. There is a minus end, which is here. Monomers will come and bind to the plus end and unbind from the minus end. This process by which you renew the filament is called treadmilling. So there is polymerization at the plus end. So there is a rate of polymerization that I will call Kp. And what I will use is not the rate of polymerization, is what I will call the polymerization velocity. Vp, which is the rate of polymerization times the size of a monomer. The important thing is the order of magnitude of that. It's between 1 micron per second and 1 micron per minute. So monomers adhere and they detach from the other end. They detach with a rate which I call Kd. That's at the minus end. The rate is Kd, and typically it's 1 second minus 1. So these are the main properties of these actin filaments. The third property on which I want to insist more is that the actin filament is a semi-flexible polymer. Sorry, I didn't hear the question.
It says KD and then something.
1 second minus 1. This is the order of magnitude of this KD. How many of you know what a persistence length is? Almost everyone, so that will go fast.
Polarization in absence of any factor?
So, yeah, I can add something. I said, okay, I'll go beyond what I wanted to say. I said there was an ATP molecule that was trapped in here. When the monomer is polymerized, the ATP molecule is hydrolyzed, so it consumes energy. So the polymerization-depolymerization process of actin is a non-equilibrium process. So that's non-equilibrium. Other question is Zvonimir's question. In general, there are proteins that help actin polymerization. These are the proteins that I was calling actin polymerization promoters. I will show you some of them in a minute. I don't want to discuss them now. So this semi-flexible polymer, at 0 temperature, the polymer will be stretched. So the ground state is a straight polymer. Something like this. And if you bend it, it's like this cable here. It costs energy to bend the polymer. And the energy is just the elasticity of the material, which is here. Now the bending energy F. So I will scale it by kT because I want to talk about thermal fluctuations. Put a factor 1/2 as any one. And then the idea is that you want to make an expansion in powers of curvature. The filament is symmetric, which means there is no spontaneous curvature, so there is no linear term. And the first term is a term proportional to the square of curvature. So there is curvature squared. I have to sum over all the filaments, so I call S the length along the filament. I sum over all the filament from 0 to the length L. And then there is a prefactor missing here, and this prefactor is the persistence length. So what the persistence length is in this language, it's the bending modulus of the filament, scaled by kT. For actin, depending on the condition, the persistence length is between 10 microns and 15 microns. Now a difference maybe with what you've heard on polymers like DNA is that in a cell, the actin filaments are short, they are a few microns long. So the length of the filament in general is small compared to the persistence length. So L, which is the length here, is smaller than LP. What this means is that the filament is almost straight, but it has small thermal fluctuations that bend it locally. So the picture that you should have is a filament like this. And it's a little bit shorter than it would be if it were straight, because I use lengths to make these wiggles here. Now, what I want to discuss briefly is the mechanical property or the elasticity of actin filaments. So the first mode I can consider is the macroscopic bending of the filament. So I take a filament like this, and I bend it with the force F. I displace it by a length x. If the force is small enough, F is proportional to x, and there is a stiffness such that F is equal to kx. I'll call it kappa. Now you can calculate kappa easily. I will just guess it. This is bending, so it has to be proportional to the bending modulus. So kappa is kT LP, which is the bending modulus, which is defined here. And then kappa is the force per unit length. So it's an energy divided by the square of a length. The energy is kT. This is one length, so I should divide by the cube of the length. Now there's a prefactor. I even forgot what it was. Maybe there's a factor 1/2. It's easy to get it just from mechanical argument. So that's the first mode of deformation. The second mode of deformation is stretching, so that's bending. So the second mode is stretching. So I take a filament like this, and I apply a force on both ends, and I pull on the filament. The filament stretches because you have length which is stored in here, and when you pull on it, what you do is you stretch, you unfold the fluctuations. That's what gives the elasticity. Now again, so I should define R, which is the actual length of the filament. At 0 force, the length is R0, so I define X equals R of F minus R0, which is the distance in the absence of external force. And again, if the force is small, F is kappa times X. Now, I have to guess what I put for kappa. It turns out, and I will tell you in a minute how you will get that this kappa stretching is proportional to LP squared. So there will be KT that is LP squared. And then you have to divide by the right power of the length of the filament. So you have 2 power here, you have to put 4 on the bottom. Now why is this stretching spring constant proportional to LP squared? So Christina explained to me that I have to use the middle one, this one. The first thing is, so I look at this filament, and to make things easy, I will do it in 2 dimensions. Now you can think about it and do it in 3 dimensions. It doesn't change anything except for a factor of 2 in the end. The way I will describe this conformation of the filament is by the local angle of the tangent. So I call theta the angle of the tangent here. And theta depends on the position of the filament. So theta is a function of S. And this is why it makes it easy. The curvature is just a derivative of theta with respect to S. So the curvature C is d theta ds. Now what I want to write is the energy of this filament in the presence of an external force. So I have 2 terms. F is the bending term, 1/2 and then I have the work of the force. The work of the force is just minus F times R. And R is sum from 0 to R of dx. But dx is ds cosine theta. So this is 1/2 of KTLP, sum of 0 to L ds. C squared is d theta ds squared. Minus F So this is the energy of this famous problem due to Euler, which is called the elastica. If the persistence length is long, the angle theta is always small. So what I can do is expand this term here, and cosine theta is just 1 minus theta squared over 2. And then the problem is simple, because this energy is a quadratic function or a quadratic functional of theta, and you can calculate any average you want just by using equipartition of energy. I won't do it, but the right way to do it is to go to Fourier modes. If you go to Fourier modes, you get rid of the derivative here, and then you can calculate every average you want. In particular, I can calculate the average size. The average of R. R is just average value of sum of ds cosine theta from 0 to L. I do the same expansion as before. The 1 gives me the stretch length. So this is L minus average value of sum from 0 to L, theta squared over 2 ds. Now, if you have a long polymer, you will find that theta squared doesn't depend on the position. So you will just get L 1 minus theta squared over 2. You calculate theta squared from this energy, you put it into here, you linearize that small force, and what I'm claiming is that the answer that you get is proportional to LP squared. I won't do it, I just leave it to you as a homework. So the homework is to calculate only this theta squared, which is here. So that's what happens when you pull on the polymer. You can do the reverse experiment. You can push on the polymer. So instead of stretching, I will look at compression of the polymer. So who tells me what happens? So I take a rod like this. I push on it. For small force, I'm playing with the fluctuation. So there is a spring constant, which is the same as on stretching. And then I increase the force. What happens? It buckles. So if you push too much in the compression direction, what you do is you buckle the polymer. And the critical force for buckling, if I ignore the fluctuations, is proportional to LP to KT, and then it must be a force, so it's like KT LP over L squared. And then there is a prefactor that depends on the boundary condition, some pi squared or pi over 2 squared, something like this. So if I try to plot the deformation of the polymer, so what I call X as a function of the force. So X is R minus R0. If F is positive, I stretch. If F is negative, I compress the filament. There is a finite slope here, which is this modulus, the spring constant that I calculated. If I go to very strong force, the filament is inextensible. So I saturate at a stretch filament. So there is an asymptote here, where I fully stretch the filament. If you play the same game that I was playing here, you can calculate how fast you approach the asymptote, and you can check that dF dL is proportional to F to the 3/2. So the more I stretch, the stiffer the polymer. If I go in the other direction, I reach a critical force here, which is Fc, the buckling force. And in all of this region on the left, the polymer is buckled. Now, if you ignore fluctuation as I do, the buckling transition is a real transition. If there are fluctuations, I don't exactly know what happens. What I would claim is that it smoothens the transition. And then you would have to worry on what happened in this region. The only reason why I want to plot this curve is to show you that it's very asymmetric. If you pull on the polymer, you make it stiffer and stiffer. If you push, you compress the polymer, you reach this buckling transition, and the stiffness essentially goes to 0 here. So what happened on stretching is completely different than what happened on compression. And that's the only point I wanted to make. Is everybody happy with that? Okay. As I said, doesn't want to come back for some reason. What do I do? I have to push. Which one?
The remote on the table.
The remote on the table. This one? No, this is a pointer. What do I do? I want to show something here. If I hit any key. No, but I have something here. I see. I know what happens. It will come. Voilà. So what I told you about so far is what happens with one actin filament. Of course, what I want to do is look at what I call the cytoskeleton in a cell. And the cytoskeleton looks like a normal mesh, like this or like this. Now, in my language, something like soft matter language, this is a gel which can be cross-linked, and it can be cross-linked by proteins like the one which are here, alpha-actinin, filamin, or other proteins like this. So that's one option. Either it makes a gel like this, or it makes bundles. And there are proteins that force the actin filaments to be parallel. If these proteins are present, they will force actin to make bundles. I will ignore the bundles and try to discuss mostly the gel. Okay. So that's actin gel. So if I draw my own picture of that, a very sketchy picture, it's actin filaments which locally are straight, that are crisscrossed like this, they are intermingled if you want. And there is essentially one length scale which is the mesh size of the gel, and I will change I will call it small l. Now, typically in a cell, small l is small. What I mean by that, it's of order 200 nanometers or less. So the length of the filament is much longer than that. And in fact, I can consider that the filaments are infinite and consider only the actin at the scale of this small l here. Now, what I care about, because afterwards what I want to do is look at the elasticity of the cell, is what is the shear modulus of this actin gel. Now, I know you had a lot of talks on elasticity and elasticity of gels like this. I don't want to go into these fancy descriptions. The only thing I want to do is give you an extremely qualitative argument on what the modulus of the gel could be. So I call that mu. And I write it as a scaling law. A shear modulus is an energy per unit volume. So the energy is kT, because whatever I do, the elasticity of a single filament has an energy scale of kT. Then I just explained to you that the only length scale in the problem is small l, so I will write it as kT over L cubed. This has a dimension of a shear modulus. And then it has to be a function, at least of the bending modulus. Now, if I want to write it in dimensionless form, I will write it as a function of Lp over L. And if there is only one length scale in the problem, whatever my theory will give me, in the end, I should find a law like this. And then I told you that there are only two ways by which the actin filament can deform. Either they deform by bending, or they deform by stretching. So if bending is dominant, I know that the main mode of deformation is bending, and I show you that the spring constant is proportional to Lp. So whatever I do, this function is linear in Lp. And the shear modulus mu is kT Lp over L4, and there is a prefactor that I don't want to calculate. Yes?
What gives this between these bundled together, just that it's very entangled?
They are very entangled. I shear them, and I ask what is the relationship between the stress and the deformation, and that's the shear modulus. Okay, everybody see how I got that? Of course, if I shear it, some of the filaments are stretched, and there is also a contribution from stretching. So if stretching is dominant, I showed you that the spring constant is proportional to Lp squared. So this is Lp squared over L squared. So mu is kT Lp squared over L5. And then, of course, one needs to have a complex discussion on when is bending dominant and when is stretching dominant. I won't do it. I leave it to people like Vincenzo and all the people I told you about in the first lectures. There are two questions I want to ask. The first one is, I cheated you somewhere. Where? And the second one, and I don't care which one because they more or less give the same answer, is I want to calculate an order of magnitude to tell you what the elastic modulus of a cell should be. So why did I cheat you? Does anybody see that? Sorry? So I said that there was only one length, and that's indeed where I cheated you. So why are there other lengths? So can you give me other lengths? Sorry? There's the length of the polymer itself. This one doesn't count. I can assume it's infinite. I mean, I told you it's a few micron. It's at least 10 times the mesh size. So this one I don't care. Yes? There's the thickness of the polymer. Oh, I didn't talk about that. That's a nice question. I can come back all the way here. Where does the thickness of the polymer count for a polymer like this? It's hidden somewhere. Can you tell me where? Who asked the question? You did. It's hidden in Lp. Okay, let's do that. So what's Lp? This polymer as a material, it has a Young modulus, and its elastic properties have to be proportional to the Young modulus. Okay? Then, when I defined Lp, I put arbitrarily a kT in here. So whatever I do, I should find back the kT here. So it's E over kT. And then I need to have something which is homogeneous to a length. For a single polymer, there are only two lengths, the radius and the total length. you agree with me that the local bending modulus cannot depend on the total length. So the only thing I can have here is the diameter of the filament, or the radius of the filament, and I have to put a force power here. And then there is a numerical prefactor that depend on the Poisson ratio of this material and things like this, but this is of order 1. So if I want to calculate the persistence length of a filament, I should do it like this. For instance, second homework, this one is trivial. You can calculate the persistence length of a spaghetti. How much should I find? A small number or a large one? Sorry?
It depends on the cooked.
I can't.
Or uncooked. Dry.
Oh, doesn't matter. Cooked or uncooked, I always get this question, doesn't matter. Or there's a factor of 10 between the two, maybe 100. Doesn't even count. So what I'm doing here, what LP does, is that it measures the influence of thermal fluctuations. You can do all the experiments you want. The influence of thermal fluctuation on a spaghetti are completely negligible, even if it's cooked. Now, another interpretation of the persistence length is that it tells you the memory of the orientation. If I fix the orientation of the filament here, how far do I have to go before it loses this original orientation? As thermal fluctuations don't count, it will remain fully straight. I forgot what you find, 40,000 kilometers or something like this. So that's a completely stupid problem. However, if you put reasonable numbers for actin, you have to choose E, but people have numbers of the Young modulus of proteins, I don't know, 10 to the 7 or something like this, you will get the right answer in the end. So even this naive formula is kind of okay. So back to here. Which lengths are missing? LP is here. I said there were only two, LP and L. So there is one dimensionless variable. So I told you that the polymers are entangled. There is a length that characterizes these entanglements, which people call the entanglement length, and this one is far from being trivial. There are lots of work on that by people like Dave Morse or Fred McIntosh. Maybe you worked on that as well, I don't know. That's far from trivial, and it counts because some of the entanglements are trapped, and that you should include in the modulus. So there is the entanglement length. It's larger than L by a factor, I don't know, 10 to 100 or so. There's another one. Suppose you take filaments of given length, you mix them. If they are too short, they don't feel the entanglements. They behave as isolated filaments. Beyond a certain length, they start to feel the entanglements, and there is a modulus. This crossover length is what I call the entanglement length. And that's highly non-trivial. In other words, what I forgot here is topological constraints. So there's another one which I didn't discuss. I told you there were cross-linkers. Now the cross-linkers are molecules, protein, that bind two filaments at a point like this. Now the distance between cross-linker is also a length of the problem. And in fact, if you want to have a solid material, you need very few cross-linkers because the actin filaments are very long. So the other one is the distance between cross-linkers. Sorry? No, the mesh size is purely geometric. It's 1 over L squared, more or less. So the mesh size is just geometrical length. The fact that this one hits a filament here and then will hit one very far away from here, that's the topology of the problem. And they both count. The fact that you have cross-linkers and the fact that you have topological interaction if you want. Yes?
Do you mean like along a filament?
Along a filament, for instance, yeah.
So not the other
So this one is cross-linked here, and then it will be cross-linked here.
That's why it's different.
Of course, it should percolate, otherwise.
And how does this length of the tail with this parameter that measures
I don't want to go into that, and I don't know how to do it properly. So, no, these are real hard problems. I just want to mention them, but they are real hard problems. So the only thing I want to do is give these naive estimates, and these gives a reasonable order of magnitude of mu. So there's a factor of 100. I'll give you a range which is just 100. Now what you want to do is use these two formulas. As I said, KT is 25 degrees, LP is 10 microns, L is something like 100 nanometers or 200 nanometers. What you get is that the shear modulus, mu, goes between 100 to 10 to the 4 Pascal. So that's the shear modulus of the actin gel at the concentration where it is inside the cell. Now the question is, do you know any other material which has a shear modulus of order between 100 and 10 to the 4 Pascal? What's this? Wood, how much is it? Sorry? Hundreds of gigapascals even. So that's way too big. The rubbers, my shoe for instance, how much is it? 10 to the 5, 10 to the 6. So it's 10 to 100 times smaller than that. Can you give me a material that does that? All these jellos, I don't know if they are English people, I don't want to do like Sonimir and criticize, but English eat these jellos at breakfast, this stuff that shakes, and then you cut it with your spoon. This is the consistency in this range here. Oh, sorry, no, you're not English, it's okay. Your wife is, but not you. So that's the consistency of the actin gel. What this means is that if this is what fixes the elasticity of cells, if I look at the elasticity of a single cell, I should find an elastic modulus which is of this order of magnitude. I'm sorry.
this wide range is without playing even with this cross-linker spacing. That presumably can be even more.
That can change it more. It turns out that this is the right order of magnitude, which doesn't mean there is no cross-linker, but it's kind of a hand-waving way to calculate it if you want. The last point I want to discuss is viscoelasticity. So how many of you know the Maxwell model? Almost all of you. Now, if there's no crosslinker, this actin gel is a fluid, so at long times it flows, and the only thing I calculated here is a 0 time shear modulus. If I wait long enough, it flows, and there is a viscosity. Now, if there are crosslinkers, in general, the crosslinkers are not permanent, which means they bind and they unbind. And again, at long time, it should flow. So this is a short time modulus, but at long time, and it flows because the lifetime of the crosslinks is not infinite. Now I want to comment on that. How many of you know polymer rotation and things like this? If you look at synthetic polymers, polystyrene or stuff like this, it flows at long times, but it flows because the polymers get disentangled. the time for disentanglement, if you're not too close to the glass transition, is pretty short. For these actin gels, the time for disentanglements is seconds, or tens or hundreds of seconds. The reason is the relaxation time is not the disentanglement time. It has to do with the lifetime of the crosslinks. So that's what fixes the time to relax stress. And typically in experiments, it's between 10 and 100 seconds. So all these proteins that were here and that disappeared, like filaments, actinin, or whatever, they act as crosslinkers. These are crosslinks with a finite lifetime, and the relaxation time of the stress that I call tau is the lifetime of these crosslinks. Now, if I know the elastic modulus and the relaxation time, I can calculate the viscosity, and just by dimensional analysis, the viscosity is eta is mu tau. I told you this is 10 to 100 seconds. The modulus is between 100 and 10 to the 4. Typically, this is of order 10 to the 5 Pascal seconds. So what I'm telling you here is that if I wait for a very long time is not so long, this is larger than a minute, the actin gel flows like a liquid, and the viscosity is 10 to the 5 Pascal seconds, which is very high. Water is 10 to the minus 3, so this is 8 orders of magnitude larger than water. Is that okay for everyone? So we stop 5 minutes, and then we...
When we were talking about these crosslinkers that they bind,
Yes.
define, is it possible to basically combine this crosslink length with the entanglement length?
Yes.
And then,
So there's a nice model that does that. There's a paper by Leibler and Rubinstein.
oh, okay.
They call it sticky reptation.
Okay.
You should look at that. That's very nice.
yeah.
The idea is that, of course, if you have a polymer with many stickers,
Yeah.
it will be bound here, but that sometimes this one goes away. So by fluctuation, it can move a little bit,
And then
then it
stick
binds to
again.
another one,
Okay.
and the time becomes very long.
Oh, nice. I guess Larson had one paper also that just did a kind of a friction type reptation. That when you,
I don't know
there's
this
always
one.
a friction force. Okay. Yeah. That's
I know Leibler and Rubinstein.
okay. Okay. Thank you very much. Thanks.
Hi.
I have one question. I mean, that looks fascinating to me, this short lifetime of the crosslinkers. Is it
Well,
because
that's long. That's much, much longer than any molecular time.
okay?
I mean,
So
the
but-
molecular
but I mean,
time would be
you-
10 to the minus 6, 10 to the minus 7
One could
seconds.
imagine that you build up a scaffold in the cell that is really fixed, right? I mean, but the cell wants to grow, right? Is that the reason? What's the biological reason for that time scale?
Because it needs to flow. I'll show you an example where it flows.
Okay.
And
Yeah,
where
yeah,
experiments
so basically
show
my
it.
question is about the biological. I mean, what are the biological?
I'll show you an
implications?
example. During this cytokinase stuff, it flows.
Do you need to erase the board?
Yes, I do. I will erase here.
The upper one?
All of these. Yeah. Oh, you do it?
Huh?
You are doing it?
Yeah, I
It's
do.
even better for me. Hi. Yes.
Module what we talked about. So you still have it under shear, and that's why it goes
Yes.
both ways. So you keep the shear constant, and it's like
Or keep the stress constant. I measure the shear,
okay,
whatever.
it's like a relaxation
Yes.
experiment. So you keep the shear
Yes,
constant, and it then
exactly.
flows.
Okay.
Okay. That was my question when you said.
Yeah. That's what this time is measuring.
Okay. Thank you.
Yes.
Does that say distance between
Entanglements.
entanglements? Okay. So
I'm sorry, I
that's
don't
different from the entanglement length.
No, that's the entanglement
That is
length.
the entanglement length. Okay. So what's the second cell?
Oh, the fact that if I put crosslink here, I distribute the crosslinks randomly. The next crosslink on the same chain will be far away,
Yeah.
and it's going to be larger than L somewhere here.
But it looks like so these are is this the same scale or
No.
two separate?
Because this one, the distance between crosslinks, I just tune the concentration of crosslinks. So it's chemistry. The other one is entanglement, so it's topology.
Oh right. Okay.
Okay?
So crosslink is
One of them I know how to tune. The other one is much more difficult. The entanglement length is hard to.
like another object that bonds or creates
Another
a
protein,
between.
yeah.
Okay.
Okay? Sorry?
Do moments of like, I don't know, distribution of mesh size matter at all? Or
Oh, it doesn't if the length is much, the average length is much larger than that.
But if you have like a distribution of
Yeah, so
mesh sizes,
if you do it naively, you find a distribution P of L, big L, over LC. You say it polymerizes at one end, depolymerizes at the other end, and it leads to that. Why? Yeah, so I have to introduce.
just from it's just the Boltzmann factor, right?
No, you say on the one side there is a rate of addition, on the other side there is a rate of, and so you write D, you discretize time, you say P of n plus, P of t plus dt, and L is equal to, and then there is all the ones that you get by addition of a monomer, all the ones that you get by subtraction of a monomers.
Detailed balance.
You look for, detailed balance. You look for a steady state and you get that.
Yeah.
Okay?
But that's just, I was wondering if the variance in the distribution of mesh sizes could be important. So like, or the,
As long
if you look at a different region of L,
as the average mass is larger than that, it doesn't count. Or it counts very little.
like the moments of the distribution should matter.
Or the moment is of order LC. The second moment is LC squared.
Wait, so is this for like, L here is the length of a polymer.
Is the length.
It's not.
Oh, the
this.
fluctuation of that.
Yeah.
Well, these are concentration fluctuations. Then, yeah, of course they exist. They don't matter very much. They don't matter very much. The ones you have in mind is fluctuations in L.
Yeah.
That's concentration fluctuations.
Good. It seems like the fluctuations that last time.
Yeah, that's because you take this stuff too literally. I mean, L should be some kind of correlation length, and then.
Dealing with this DNA molecules that they also do semi-factor.
Yes.
And I mean, when you're talking about, for example, the stretch modulus of the single
Yes,
strand
but
versus
DNA
double strand, I mean, that LP, that persistent length,
That's of the whole polymer.
but it's the other way around. I mean, when you
No, but,
stretch the double strand,
it's stiffer.
stretch
It's more.
is it
It's more
stiffer
rigid.
or
It's more rigid.
But in the experiment that they showed, I mean, basically the
Or
K
the different-
value is less for the
Or
double
because
strand compared
sorry,
to the single strand.
K is what I call 1 over K. Then
Okay.
it's as stupid as that, I would say.
But if I guess this is just if you can't find someone on the fridge. I had no idea who he was.
Should I start? They're coming back.
I just did that for some reason. Excuse me, we have staff.
Can we start?
Thank you. Is your microphone on?
Is there what?
Is your microphone on?
I guess so. So let me start back. What I told you is that I wanted to discuss the actomyosin cytoskeleton. I discussed actin. What I want to do now is discuss molecular motors. So I won't say very much on molecular motors because what I wanted to say is almost exactly what Zvonimir told you yesterday. So I will say the same thing but in my own language. And as you see, the movie is exactly the same here. So molecular motor, this is a molecular machine. So one protein. That consumes energy. And creates either force or motion. Now, energy consumption. You know that in a cell, energy comes from ATP. And there's a simple chemical reaction that I will write. So ATP, adenosine 3-phosphate, can lose a phosphate and become adenosine diphosphate. So this gives ADP plus 1 phosphate. The main point is that in a cell, this reaction is very far from equilibrium. What I mean by that is that there is a huge excess of ATP. And that the cell has a machinery because, for instance, you eat sugar, and sugar is transformed into ATP. They have a machinery to produce ATP and to maintain the level of ATP constant. So in everything that I will say, ATP is consumed, which means ATP is a fuel, it becomes ADP. But then you give energy to the cell, and the energy that you give to the cell maintains the level of ATP. And that's how molecular motor gets their energy. Now, this reaction is called a hydrolysis. Every time you hydrolyze one of these molecules, you recover the energy difference between the two sides. That's what I will call delta mu. Now this delta mu depends, it's a free energy, so it depends on the concentrations of ATP, ADP, and phosphates and stuff. In a cell, in the conditions of a cell, the value of delta mu is something like 25 kT. So that's where molecular motors get their energy. They trap an ATP molecule, it's hydrolyzed, and that provides energy to the molecular motor. The second thing is, and you see two, yes? I can't hear you, I'm sorry.
Do you know how much of that energy is actually converted into?
Oh, that's an interesting question. So what's the yield or the efficiency of a molecular motor? It's extremely high. The first thing is it is a fully non-equilibrium system, so there is no upper bound as you would have in thermodynamics for macroscopic engines. So it could be as high as you want. Typically, the motors that Zvonimir showed yesterday, kinesins or myosins, have an efficiency of 45% or so. Yeah, and there is even one, I'll show you in 5 minutes. There's one which is supposed to have an efficiency of more than 80%. So they are very efficient motors. So the structure of these motors, it was here and it disappeared. It's in the other direction. So you see a typical motor here. It has two heads, that walk on the filament and one long tail. So I will sketch it like this. This is one head. Second head is like this, and one long tail. And they walk on the filament. Now, whatever you do, if you want the motor to walk in one direction and not to diffuse, you need to break symmetry. Something has to break symmetry. And the only way to break symmetry is that the filament is polar. So you can only have molecular motors on polar filaments. Now we'll show you. Sorry? Well, single one doesn't. If you couple motors together, they can spontaneously break symmetry, and then the filament can be polar. But if you have only one machine, I don't know of any example where the motor itself would break the symmetry. But by coupling many motors, you can do that. So I'll show you an example. So one of the roles of molecular motors is to transport materials in a cell. They walk on the filament. There's a big vesicle bound to the motor, and it transports material. This is the example that Zvonimir showed yesterday, which was kinesin working on a microtubule. So I have a... what happens? So this is the molecular motor, which is walking, and it's carrying biological material inside the cell. If you use molecular motor, you do transport by convection and not by diffusion. And if you want to go over large length scales, this is much more efficient. I can show it again. It disappeared. So these are the two heads. They are walking on these microtubules, and it's carrying this material, which is here. There are a whole bunch of interesting physical problems. In general, there are many, many motors on the same filament. There are traffic jams with molecular motors, for instance. And there's a whole bunch of problems associated with traffic jams with molecular motors, which we spent some time studying a few years ago. I have to get rid of that. And of course, the microtubule is polar, which means that each motor always walks in the same direction. I told you that actin had a plus n and a minus n. Microtubules also have a plus n and a minus n. And these kinesin motors, this one, always walks to the plus n. So motors are directional. The last point I want to make, which was also discussed yesterday, is the difference between processive and non-processive motors. Now, these motors that I showed you makes many steps on the same filament. It's processive. And the fact that it's processive is that it makes many steps. Typically, these motors will make 100 of steps. So it will travel 1 micrometer, then detach from the filament, and then come back and have cycles like this. And you can carry material over very long distances, in particular in your brains or along your axons. You need to carry biological material over almost meters. So these are processive motors. Now, what I will care about today is non-processive motors. So the non-processive motor is this one that you saw yesterday. I will show it again. So My stuff is not very nice. So it binds to the filament, it gives a kick, and then it will go away. So there is a ATP cycle which is going on, and the motor detaches. And that's it. So you cannot use a single motor like this because it will go on, make one step and go away, and you do nothing like this. So the way nature uses these motors is that it makes clusters of motors. So they are bound by the tail. I will make a sketch of that. So the tails of the motor are all bound together here. And the heads are here. Now the idea, and this is in muscle, it's called the SIG filament. The idea is that if you have an actin filament below, I can draw it in white. This motor will bind and then give a kick, then it goes away, but another one can bind and give a kick, and so far and so forth. So if you have enough motors in this SIG filament, there is always at least one motor bound, and this aggregate of motor can operate. So the idea is that you have to make aggregates of motor so that there is always one motor in contact with the actin filament. Is that clear or not? Yeah? Now this is how maçons work. And in maçons you have these clusters which are called SIG filament. Typically you have 300 myosin motors. And then these 300 motors can move with respect to the actin filament, and that what drives the contraction of your muscles. Now, in the cytoskeleton, what you have is smaller motor clusters. They are called mini filaments of myosins. Typically, they will have between 10 and 20 myosin motors. So, on the same filament, you have many motors. Some of the motors can bind one actin filament. Some of the motors can bind another actin filament, and then they pull on them. So what the motors do in the cytoskeleton is they create internal stressors in the actin gel. I have a sketch of that. This is the kind of actin gels that I'm talking about. Here is a cluster of motors here. The motors which are on this side bind to this filament here. The motors which are on this side bind to this filament here. The motors exert forces, and then you create internal stresses in the gel. One of the points I want to insist on is that you do that, but you do that by consuming energy. So it's always a non-equilibrium process. Now there's the last thing that I wanted to show you with respect to what Zvonimir was showing yesterday. He showed you these gliding assays. So you bind myosin motor by the tail, and you put actin filaments on top of it, and you see the actin filaments moving. I will show you one, except that at the beginning of the movie, the motors don't have any ATP. So nothing happens. There is no energy source. The motors don't work, and the actin filaments don't move. At some point, and you would see a flashlight coming in, this releases ATP, the motors get their fuel, they start to walk, and the filaments can move. So that's what I want to show you. So here nothing happens. Completely nothing happens. Nothing happens. You see this light coming in here that gives ATP, and you see the filaments moving. So that's kind of a direct proof that the motors work only if you give them energy, and the energy is this chemical energy that comes from ATP. Again, each of these long filaments interacts with many myosin motors, and at each time there is at least once which is in contact with the filament. It gives it a kick, and that's what pushes the filament. Is that okay? I don't want to say more about molecular motors. The important things are here. They consume energy. They always walk in the same direction. And in the cytoplasm, they are non-processive.
Is there any scope in inquiring about elastic deformations?
So yes, some people, for instance, suppose, not with myosin, at least not as far as I know, but suppose you look at a kinesin on a microtubule, it might deform the filament a little bit, and then it might interact via this deformation with the neighboring motors.
Are these things so tiny that it's an academic thing?
No, it seems to exist. Some people are trying to study that. And there are experimental claims that this is something that counts.
And an even simpler question. Presumably there can be also phonons propagating on this tubes.
Yes.
Yeah. These objects are chiral,
Yes.
the background. Does that cause some interesting things about?
That I can't answer. The thing that I can answer is the actin filament is chiral, that I said, so the motor turns like this. So there is a Japanese guy who was able to label the motor, and you see it turning around the filament like this, because it follows the chirality of the filament.
Right. What I'm wondering whether the elastic deformation.
No, I understand. I can't answer that. But yes, I would say with actin it doesn't count so much. With kinesin on microtubules, you can have deformation modes of the microtubules, and these might be interesting effects. So what I want to do now is try to describe the whole cytoskeleton, which means actin plus myosins. I told you it's a gel, but it's a non-equilibrium gel, where I want to take into account two effects. The first one is the fact that it consumes energy via the molecular motors. And the second one is the treadmilling effect, the fact that it polymerizes and depolymerizes all the time. Before I do that, what I want to show you is that indeed the cytoskeleton is a non-equilibrium system. So I will describe an experiment to you that checks that the cytoskeleton is a non-equilibrium system. So the best way, or one of the best ways, because there might be others, to check that the system is non-equilibrium is to check for the fluctuation dissipation theorem. If the system is at equilibrium, the fluctuation dissipation theorem should be satisfied. If you find a violation of the fluctuation dissipation theorem, it means that the system is out of equilibrium. So that's what I want to show you now. So the idea of the experiment is to take an active gel with molecular motors, so a piece of actomyosin cytoskeleton, And then inside that, you introduce colloidal particle beads. Now you need to make them larger than the mesh size. This is my bead. And not me, but Christoph Schmidt, who is the one who did this experiment, did in fact 2 experiments. He took one direction, x here, and he measured the fluctuation of the position of the bead in this direction. So x of t is the fluctuation of the bead position. Now what you do is you calculate the correlation function, x of t equals 0. You average that, and you calculate the power spectrum, which means you calculate the Fourier transform of that. Sum e to the I omega t dt from 0 to plus, from minus infinity to plus infinity. That's what I call the power spectrum. So that tells you how the bead fluctuates inside this actomyosin gel. Then you do a second experiment. You put an external force. F at a frequency omega, which means a force F cosine omega t in the x direction. And you measure the position of the bead at the frequency omega. If F is small enough, it's proportional to the applied force. So x of omega equals some response function, chi of omega times f of omega. And chi of omega is what's called the response function. Now, if you have a complex material like the actin gel, the response function is complex, so it has a real part and an imaginary part. And you know, because of causality, the real part and the imaginary part are related by this Kramers-Koenig relation. Now, whatever the system, and in particular in these active gels, chi prime tells you about the energy you store in the system, and chi double prime tells you about the dissipation. It's like when you do electromagnetism, the imaginary part of the dielectric constant tells you the dissipation in the system. So this chi double prime tells you how much energy you dissipate when you apply this force F. Yes? Yeah, both of them depend. Yes, you're right. I should have written both. It's not that I could have. If chi double prime depends on omega, chi prime must depend on omega because of this Kramers-Koenig relation. Now, what the fluctuation dissipation theorem tells you is that in a system at equilibrium, these two experiments are related. So for an equilibrium system, C of omega equals 2 kt over omega chi double prime of omega. What this tells you is that the dissipation of this in the system, which I said is measured by chi double prime, is directly proportional to the fluctuations in the system, which are measured by a power spectrum C of omega. Now, then the experiment is easy. You actually do these two experiments. So you put a bead, you measure its fluctuations, then you put an external force on the bead. You do that with an optical tweezer. You oscillate the optical tweezer. You measure the response function, and you plot the ratio between omega, C omega divided by 2 chi double prime of omega. And this is either kt or not kt. So let me show you what it does. don't know why. So this is the imaginary part of the response function. This is the fluctuations. You see that if you go to high frequencies, above 10 hertz, they're identical. They're identical because they divided this by 2 kt over omega, so the ratio should be 1. At large frequencies, they are the same. So at large frequencies, the system is at equilibrium. It's not a big surprise because at large frequencies, you probe only very small length scales. So you probe individual actin filaments, and molecular motors are not fast enough to interfere. So you can even calculate the shape of this curve, and that fits pretty well. If you go to low frequencies, below 10 hertz, you see that the fluctuation, the power spectrum, is much larger than the imaginary part of the response function. So here, molecular motors play a role, and the system is out of equilibrium. Now, this is a big experiment to show you that something with molecular motors that I spent 20 minutes telling you that they consume energy is an out of equilibrium system. But at least it proves it directly. Now, I have a movie to show you. I asked Christoph Schmidt, who did this experiment, can you show me pictures of the bead and see how they fluctuate? And he said, yeah, I did 2 experiments. I did one when there is no ATP. If there is no ATP, the system is at equilibrium, and the 2 curves are on top of each other here. And if there is ATP, you find this curve here. Now, the movie that I want to show you is the actual experiment. So these are the bead in the actin gel. For instance, this one is fluctuating a bit. So the extra fluctuations that I'm talking about is the fluctuations of this bead. And he only sent me 1 movie. So I asked, what about the other one? And he said, but the other one, there's nothing to make a movie of. The beads don't move at all. So everything you see here is the active component of the fluctuations in this gel. Why is it frequency dependent? Because at high frequencies, the motors are not fast enough and they don't respond, and the system can be considered at equilibrium. If you go to low frequency, you see the effect of molecular motors. The system consumes energy and it's out of equilibrium.
So does that mean that there is one regime in which this movie also looks like stuff?
So if I would go, yes, you don't see modes at very high frequencies. I mean, if you look at the jiggling of the bead, it's like 1 hertz. That makes sense. So I will show you another experiment to try to prove you that.
Is there some feature of that deviation from equilibrium that tells you more about the process?
Oh, that tells you more about why the fluctuations are different from that? This part is easy to model. This one is kind of hard to model.
Like, as you said, I mean, the fact that it's out of equilibrium did not surprise you tremendously, but maybe by looking at how much it is out of equilibrium.
So I'll show you another experiment, which doesn't have much to do with that, but last week when I was preparing that, we were working on the paper, so I decided to show it to you. Yes?
Is the external force applied directly?
So the external force is an optical tweezer. You just catch one bead and you shake the tweezer. Apparently it's easy to do. I can't do it, but apparently it's easy to do. No. So you turn off the ATP. This one doesn't change very much, and the correlations go on top of this one. That's what happens. So what it means is that it's extra active fluctuations mostly that you have. That's exactly what it says. It's not changing the response too much. It's not always the case. So my second example is a red blood cell. Now, a red blood cell is a special, so you know what they are. They are special types of cells. They don't divide. They don't have an actin cytoskeleton. They have a network of polymers, which are called spectrin, which is bound to its membrane. And there are huge debates on the literature whether the properties of red blood cells depend on ATP or not. So this colleague of mine, Timo Betts, decided that he wanted to check whether red blood cells were equilibrium systems or not. The way he does it, so the red blood cell is here. He holds it with 4 optical tweezers. These 3 ones are just very strong, and they immobilize the red blood cell. And this one here fluctuates. And this is the one where you measure fluctuations or where you exert the force. So these 3 are very strong. They just avoid that the red blood cell flips in any direction. And what you do, you bind a bead to the red blood cell, and you do exactly the same experiment. And the answer is very similar. It's here. This is the response function. This is a correlation function. And again, above 10 hertz or so, you see that there are extra active fluctuations, and that the power spectrum is much larger than the imaginary part of the response function. Now, in this experiment, you can eliminate ATP. So you put it in a glucose-free solution. You wait 48 hours. And after 48 hours, the red blood cell doesn't have any ATP. It's consumed all of its ATP. And this is kind of the answer to your question. It looks like this, which means it looks very much like this one. The reason why he did that, first of all, he wanted to check that the experiment was working. And if there is no ATP, a dead cell should be an equilibrium system. As you said, if you are at equilibrium, you are dead. It's also true for red blood cells. Also, there is a possibility that the mechanical parameters of the red blood cell would depend on ATP. And he wanted to eliminate that. So you see well here that if you have ATP, you violate the fluctuation dissipation theorem. And the conclusion of that is that the red blood cell is a living system. Despite all I said before, it's active, so. No. So then what I don't show you is we made a huge model for that. I can tell you more about that. So the red blood cell has a membrane, and attached to these membranes, you have a very nice network, which is a triangular network of this protein called spectrin. At this point here, you have a set of protein that anchors a network in the membrane. One of them is called ankyrin, and one of them is called PKC. Now what happens is that each of these spectrin filament binds and unbinds to these points here. And this reaction of binding and unbinding depends on ATP. So the non-equilibrium effect comes from the bending and unbinding of these spectrin polymers to these points here in the membrane. So the model that we made is we couple the elasticity of this stuff. I don't know. Now, the only thing I can say is we can make a model of that fits pretty well the experiment, and all the elastic constants are known because they've been measured very precisely. Sorry? Yeah, and ATP is involved at this point. What Timo Betts did, he was very smart. He went into the literature and looked at all the proteins that consume energy in red blood cells, and it turns out that there are only 4. There are pumps, there are these ones, there is no motors, and one of them is a flipase. It's something that tapes a lipid on one side and puts them on the other side. So we kind of decided that this was a dominant mechanism. We didn't study the 3 others. Yes?
You can have the implication of sufficient theory for driven systems.
Yes?
Is there a fundamental qualitative difference in those deviations that occurs in an active system from a driven system? Like if I shear something at the boundary versus
Yes.
some qualitative difference.
I don't know how to answer, but you have a violation. The way we did it, at least, you have a violation of the fluctuation dissipation theorem only if the spectrin network is pre-stressed. which means the violation is proportional to the pre-stress of the spectrin network. So the springs are under tension, if you want, which is not exactly the same thing as what you say. But in our system, it's required that the springs are under tension, which was kind of known. So my main point here is that if you want to check that the system is living or dead, one way to do it is to use the fluctuation dissipation theorem. And we like to do that very much. It's time. Good. No more questions? Okay, I'll finish that tomorrow.